All right, so we're going to work with some more counting problems, and these counting problems are going to have a feature that is going to involve complements. Now, we talked about complements, again, back in chapter 2 of our book. So do you remember what a complement of something is? It's whatever's missing, exactly. So this is the idea, and we talked about this again when we did that, is when somebody says they compliment you, it means they have features you don't have. Do you remember that? It's the same thing like that, not the compliment like, hey, you look really nice, but the compliment as in they complete some piece of you that's missing. So a complement's principle of counting says the following. The number of ways a certain event can occur is the number of total ways something can happen minus the ways it can't occur. So jot that down, and then I'm going to give you some formulas, some equations that talk about that from that perspective. All right, so what this says is that the number of ways an event, we'll call it A, can occur, is the number of total possible outcomes. This is a notation we used before, N of U, minus the number of ways it would not occur, which would be the complement. Now, I could do this same formula and have switched where the A complement and the A are. The number of ways A complement occurs is the number of ways total possible minus the number of ways A can occur. That's the same thing, but if it makes more sense to you to think about a particular situation, you can think of it from this way. And likewise, you could also say then that the number of ways that A occurs plus the number of ways A complement occurs is just the number of total ways anything can occur. And all of these are really just three versions of the same thing. You add and subtract a little bit from here or there, and you've got all the same stuff. Okay? And again, this relates back to our ideas when we were doing Venn diagrams of having a universal set U, and that's the entire rectangle that's green, the entire thing. A is the set in the center, and then A complement is the part that's on the outside of the rectangle that's not inside the circle. So if we add the part that's inside the circle and the part that's outside the circle, we get the entire rectangle U. And that's all this formula says. Now, we mentioned this 5-card poker hand last time. And the reason that this is being given to you is because we already created it. Let me remind you when we created it, where it came from. It said consider the 2,598,960 possible 5-card poker hands. When we did this before, we did that because there were 52 cards, and we chose 5 of them. So that's where that number's coming from. It's not just a magical number I made up or something like that. Okay, we actually found it once before. So 52C5 is the 2 million number right there. Okay. Now, what we are going to do in this section is that the number one thing that will help you to figure the problem out is the part that's in parentheses in this problem. Okay? Now, on some of your bookwork problems, it tells you the part in parentheses. Like, it doesn't make you fill it in like we're going to fill it in here. And on other parts of them, it doesn't even give you the parentheses as a, hey, remember this is what you're supposed to be thinking kind of reminder. All right? So it does one of the two. It either gives it to you or it doesn't say anything about it at all. The key to being able to do this particular problem is reminding yourself how you find the complement, what the complement is. All right? And when I do it on the test, I will actually force you to tell me what the complement is in order to do the problem. Because otherwise, you're probably going to forget and you're going to be stuck. But let's think about this particular problem. It says, at least one card is not a club. What is the complement? What is the exact opposite of this statement? They're all clubs, right? So that's what we're going to be looking at on this problem. We're looking at cards that are all clubs. But we're applying that formula that we just learned on the previous slide that says what I really want is I really want to have not all clubs, the number of not all clubs. But the way that I find that is I find the number in the universal set, which I was given was the 2 million number, and I subtract off the number of items that are all clubs, which I've yet to find, but I will shortly. So the only piece of this that we're actually going to find is this piece right here, right? The very piece at the end. Because we're given this piece, the number of items in the universal set, it's the 2 million number. And we're looking for this piece over here, and we're sort of finding it indirectly. We're finding the number of things that it can't be so that we can subtract and find what we actually want. All right, so you know that the first number here is 2,598,960. How do I find the number of hands that are all clubs? Okay, so what is 13 coming from, Matthew? 13 is all the clubs, but it's not just minus 13, but that's involved. How do I get a hand of all clubs? Wow, that test on Friday is looking really scary right now. Because we've already done this problem before.
50.
Thank you, Stephanie. Yes, it's 13 because there's 13 clubs. Why is it a combination? Order doesn't matter, that's good. And why is it a 5 at the end? I need a 5-card hand. Okay. Are we feeling a little bit better? Do you remember this piece? Because we've done this piece before. The new part here is the subtraction, which is really a very ordinary operation. That's really the only new part here. Okay, 13C5. How do I find 13C5? Oops. 13 factorial on top, right, Tyler?
Over 5 factorial, 8 factorial.
Looks good. Everybody remember those pieces now. All the factorial pieces okay? Good. So what am I going to do with my 13 factorial? I'm going to write 13 down till 8 because there's an 8 in the denominator that's the largest. There are 13, 12, 11, 10, 9, 8 factorial over my 8 factorial. And then the 5, 4, 3, 2, 1. All right, what simplifies?
5 and 2.
Okay, so 5 times 2 is 10. What else? 4 times 3 is 12.
8 factorial.
The 8 factorials. So grab your calculator. All you're multiplying is 13, 11, and 9. 1287. That is a number we've seen before because we've done this problem before. That part of it anyway. So we need to take 2,598,960 and subtract 1287 from that. What number do you have?
2,597,670.
Any questions on that? Okay. So the goal in doing all of this is filling in the piece that's in the blank where I wrote all clubs. And then it's finding the combination or the permutation depending on the problem and how the problem is structured. This problem is going to be combinations because it's cards. And so finding that quantity and then subtracting. All right? So we're really just adding on this idea at the beginning of filling in a complement and this additional feature at the end where we subtract it from something. That's the new part of this. That's all this new part, because everything else we've done. All right, this one wants to know how we would get cards of more than one suit. What's the complement of getting more than one suit?
Using one suit.
All the same suit, all of one suit, right? So this would be all the same, or you could say all of one suit. Okay, so again, I'm finding n of A, which is n of U minus n of A complement. And the complement's the part that's in parentheses. N of U is still the 2,598,960 that I had a moment ago. All right, the A complement. How do I get all the same suit? What does that mean? All 5 cards are what?
One suit.
Okay, so all 5 cards are maybe clubs, or all 5 cards are hearts, or spades, or diamonds, right? But they're all 5 of the same variety. All right, well, we already found out how to find all 5 clubs in the previous slide, didn't we? Okay, there's 1,287 of those, right? So 13C5 gets me all of the same suit. But how many suits are there? There are 4. So you can either write down that this is times 4C1 or it's just times 4 because there's 4 suits. I actually have to multiply by 4 because there's 4 times as many of these kinds of cards because there's 1,287 of these that are clubs, there's 1,287 that are hearts, there's 1,287 that are diamonds, and 1,287 that are spades. Right? And we've already found that 13C5 is 1,287, so we're not in. So I have that same 1,287 from the previous slide times 4. So what is 2,598,960 minus 4 times 1,287? It's still 2 million. Say that really loud for me, DJ. Perfect. So there's still 2,593,000 ways to get different suits in my hand that I'm working with. Sound good? Okay. At least one face card.
False.
No face cards, right? No face cards. The opposite of at least one face card in my hand is having no face cards in my hand. Make sense? All right, so the number of ways my event can happen is n of U minus n of A complement, and I know that n of U is 2,598,960. How do I find the number of ways I get no face cards? So this is kind of like the one Brian asked about up here. We had 9 classes that were possible. 8 of them were the wrong class. Here I have 52 cards to pick from, but my question is how I get them to be non-face cards. 12 is the number of face cards. So 40, right? 52 minus 12 is 40. There are 40 cards that don't have faces on them. So I would have 40, then what? C5, right? Because I'm choosing 5 cards. All right, so how do I get 40C5? What is that going to look like? Okay, so first 40 factorial, right? Yes, over 5 factorial, 35 factorial. So how far out am I going to write this 40? To 35. All right, 40, 39, 38, 7, 36, and 35 factorial. Five, 4, 3, 2, and 1. Now, there's homework that I handed back to some of you today and to some of you last time. I did not make comments on them out loud, but a few comments let me make right now. Some of you are being really sloppy. At the end of here, you get to 35 and you're just writing 35. That factorial needs to be on there because otherwise it doesn't actually mean the same thing. So it should say 35 factorial. That's actually still part of the process at this point. Now, I recognize the next thing you're going to do is you're going to mark them out, and that's great. But make sure you're marking out 35 factorial, not just 35. All right, what else is going to simplify here? All right, 40 and 5. What will the 40 become, DJ? An 8. Good. Now what?
42.
All right, that sounds good. This 4 and this 2 could cancel with the 8 that I just created. Now what? 39 and 3. What will the 39 become? 13. All right, so I have a 13, 38, 37, and 36. What is 13 times 38 times 37 times 36?
38,008.
Looks good. And then we're going to subtract. That's the largest one we've subtracted so far. It's going to bring me under 2 million.
40,000.
Perfect. 1.9 million, right? So you're pretty likely to have a face card in your hand, right? That's pretty good chances. All right. Ready for the last one? At least one diamond. Thank you, Mackenzie. That's right. No diamonds. Okay, so I want to find out the number of at least one diamond. It's going to be the number in my universal set minus the number in this complement that I've just created. So 2,598,960 minus. How do I get no diamonds?
39.
All right, so there are 13 cards that are diamonds, so there are 39 that aren't, right? 52 minus 13. 39, and then it's C5. C5, what will that look like? What was that?
5 factorial and
5 factorial and 34 factorial. That sound okay? Good. How far out am I going to write my factorial? 34. So I have 39, 38, 37, 36, 35, and 34 factorial. And then I have 5, 4, 3, 2, and 1 in my denominator. So I'm going to start with my 34. What do you guys want to cancel next?
5 and 35.
Okay, 5 and 35. What will 35 become? 7. Now what?
4, 3, and 36.
4 times 3 would be 12. And then I've got my 36 will become a 3. Great. Now what? 2 and 38. And the 38 will become a 19. All right, so this is where you have to be real careful you don't lose anybody because we've got a mess a little bit going on. I have 39 times 19 times 37 times 3 times 7.
575757.
It is. What a fun number, right? 575757. And when you subtract, it's almost equally as fun.
2023203.
2023203. Right, almost as fun. Yes, Matthew.
How
How come we didn't take the 1287 that we got and multiplied that times 3?
Because the 1287 would be the number of all diamond hands. All we want, though, is we don't want a hand that's like all clubs or all spades. We just want it to not have any diamonds in it. So, for instance, it could have 2 spades and a club and a heart. Right? So it's not wanting all of them to be a specific suit. It's just wanting it to not have any diamonds in the hand that were dealt. That's the difference. All right, so let me make one comment before you guys start with group work here. I chose an example that used the 2,598,000 the entire time. You guys get that, right? Your example that you're going to use is not going to have that because what it's going to do is it's going to flip coins. So you're going to have to create the value that starts this thing off. All right, I used something we had done before, the 2 million number. You're going to flip coins, and you're going to have 7 coins. So that everybody's on the same page, let's just talk about where we start. If you have 7 coins, how many different things can come up when you flip your 7 coins? How can you find that?
7 for each.
What did you say, Al? 2 for each coin, but then I have 7 coins, so what would I do? Multiply what, though? I'll use a bright screen here for a sec. I need a dark colored pen. So here's my 7 coins. Okay? And they're all 2s. That's what Yael told me, right? What am I going to do with these guys? We're going to multiply these together. And we saw that happen in a particular section number 2, called the fundamental principle of counting. So if I multiply all these 2's together, what do I get? It's 2 to the 7th. What is 2 to the 7th? 128. Okay. So as you start your problem with your 7 coins, it's going to ask for you some different things of you. But this is the very first number they're talking about. Because the first question is, if I create or if I have 7 coins and I flip them, how many ways can certain things happen? Well, the total number of things that can happen, period, is this. There are 120 different results that can come up when you flip your 7 coins. Okay? Make sense? Okay.